Welcome, esteemed colleagues and fellow enthusiasts of advanced astronomical sciences. In today's technical discourse, we explore the profound legacy of Tycho Brahe, a towering figure in Renaissance astronomy whose empirical observations and instrumental innovations laid the groundwork for modern astronomical methods. Our exploration will be richly detailed, emphasizing both quantitative analysis and technical refinements that underpinned his contributions to celestial mechanics and observational precision. This video will systematically unpack Brahe's life, from his noble origins and rigorous education to his groundbreaking discoveries, such as the supernova of 1572, delving deeply into the data-driven analysis of the astronomical phenomena he documented. In addition, we will examine the sophisticated instruments engineered at Hven, including the renowned Uraniborg and Stjärneborg observatories, which revolutionized pre-telescopic astronomy. Moreover, we will discuss the development of the Tychonic planetary model, critically evaluating its theoretical merits and limitations in the context of contemporary celestial physics. Throughout this presentation, expect rigorous mathematical arguments, factual precision, and exact numerical analysis that reflect the advanced state of our understanding in modern astronomy. Let us now proceed, with explicit attention to empirical evidence and robust technical detail, into the intricacies of Tycho Brahe's lasting scientific legacy. Tycho Brahe's early life represents a unique convergence of noble heritage and rigorous education that shaped his later contributions to astronomy. Born on the 14th of December 1546 at his family's estate in Knutstorp, Danish Scania, Tycho was born into an aristocratic lineage with deep connections to influential families such as the Brahe, Bille, Rude, Troll, Ulfstand, and Rosenkrantz. This privileged birth enabled him access to the finest intellectual resources of his time, yet imposed the weighty expectations of noble lineage. At the age of 2, Tycho was entrusted to the care of his uncle, Jørgen Thygesen Brahe, whose estates in Tostrup and Langland provided a nurturing and disciplined environment. Although separated from his biological parents, he was exposed to both the practical aspects of estate management and the subtleties of court life. This early immersion in administrative duties and rigorous social protocols fostered a resilient character and a methodical approach to learning. Tycho's formal education commenced at a Latin school in Nykøbing, where he mastered classical languages and texts, establishing a foundation for scholarly inquiry. By the age of 12, he enrolled at the University of Copenhagen, where he was expected to pursue law. However, his fervor for natural philosophy and celestial phenomena soon took precedence over conventional humanist studies. Early encounters with astronomical events, including a solar eclipse, sparked his lifelong passion for precise observation and data collection. The combination of rigorous aristocratic education, exposure to advanced classical thought, and early practical experience in governance uniquely positioned Tycho to innovate in the field of astronomy. His background instilled not only a strong command of theoretical frameworks, but also an uncompromising commitment to empirical data. This educational foundation and noble bearing would later manifest in his meticulous record-keeping and the development of advanced observational instruments. In retrospect, Tycho's formative years encapsulate the essential elements of social status, academic refinement, and intellectual curiosity, elements that would drive him to revolutionize observational astronomy. These early experiences are integral to understanding the evolution of observational astronomy. They provided Tycho with the necessary tools and mindset to confront existing astronomical paradigms, ultimately paving the way for his systematic approach in refining celestial measurements and enhancing the precision of astronomical instrumentation. This legacy remains profoundly influential. Tycho Brahe's academic and travel experiences played a critical role in the refinement of his observational techniques and theoretical perspectives. In his youth, after establishing a foundation at the University of Copenhagen, Tycho embarked on extensive travels across Europe to broaden his knowledge and refine his techniques. His journey included studies at the University of Rostock, where he engaged deeply with eminent professors of medicine and natural philosophy, and further exposure to the burgeoning field of alchemy. These early academic forays not only enhanced his technical skills, but also instilled in him a profound interest in empirical investigation. While in Leipzig, Tycho's encounter with innovative mathematical methods greatly influenced his approach to astronomical measurement. During his travels, alongside his mentor Anders Sørensen Vedel, he visited major centers of learning in Germany, where he engaged with scholars who were critical of traditional Aristotelian views. Such interactions fostered his resolve to seek higher precision in observational data. His exposure to continental approaches encouraged him to combine the geometrical insights of Copernican heliocentrism with the prevailing Ptolemaic tradition, ultimately shaping the methodological framework of his later work. Furthermore, Tycho's extensive journeys allowed him to witness diverse astronomical phenomena firsthand. Observations made during planet conjunctions and eclipses in various European locales provided him with critical comparisons against established tables. This period of travel was marked by intense scrutiny of astronomical events, catalyzing his shift towards a more quantitative and systematic mode of inquiry. The continuous exchange of ideas with leading scientists enhanced his capabilities in instrument design and calibration, enabling him to devise measurement techniques that significantly reduced observational errors. These cumulative experiences not only refined his technical prowess, but also cultivated a relentless pursuit for accuracy that defined his entire career beyond measure. In November 1572, during an era when the immutable perfection of the celestial realm was widely accepted, Tycho Brahe observed an extraordinary phenomenon that would revolutionize astronomical theory. From his vantage point at Hereward Abbey, he discerned a luminous new object in the constellation Cassiopeia, what we now recognize as a supernova. This event, designated SN 1572, was of such exceptional brightness that it challenged the long-held Aristotelian concept of an unchanging firmament. Tycho's meticulous measurements revealed that the star exhibited no significant parallax relative to the fixed stars, conclusively establishing its location well beyond the lunar orbit. This discovery had profound implications for astronomy. For centuries, the celestial realm was thought to be immutable, with stars and planets following divine, unalterable paths. The sudden appearance of a new star, unbound by these fixed trajectories, compelled Tycho to reevaluate the fundamental principles of cosmology. Through deliberate and repeated observations, he quantified its motion, or lack thereof, and contrasted these findings with the known planetary movements. His work provided the first robust evidence against the Aristotelian paradigm, demonstrating that celestial changes were not only possible, but observable. Furthermore, Tycho's data-driven approach incorporated sophisticated corrections for atmospheric refraction and instrumental limitations, ensuring that his measurements of SN 1572 were accurate to within a fraction of an arc-minute. His detailed protocols for calibrating observational instruments set new benchmarks in error reduction and data fidelity, pivotal for advancing modern observational astrophysics. This rigorous methodology demonstrated the viability of quantitative analysis in a discipline that had long been dominated by philosophical speculation. His careful consideration of measurement uncertainties, combined with statistical treatment of observational data, underscored the importance of precision in scientific inquiry. In addition to his observational accuracy, Tycho published his findings in the treatise De Nova Stella, a work that meticulously documented the instrumentation, techniques, and calculations employed during the 1572 event. This publication not only provided a comprehensive record of the supernova, but also served as a reference for future astronomers striving to improve the precision of their observations. By integrating geometrical reasoning with advanced empirical data, Tycho established a new paradigm in observational astronomy. His work with SN 1572 remains a cornerstone in the study of stellar evolution and supernova mechanics, offering modern researchers a historical benchmark for the evolution of scientific methodology and quantitative analysis in astrophysics. Thus, the supernova of 1572 overturned doctrines and ignited numerous theoretical advancements in celestial mechanics profoundly. With the generous patronage of King Frederick II, Tycho Brahe was empowered to transform his theoretical insights into practical achievements through the construction of state-of-the-art observatories on the island of Hven. His vision materialized in Uraniborg, the first large-scale observatory in Christian Europe, which served as both a research center and a hub for advancing astronomical instrumentation. At Uraniborg, Tycho oversaw the design and construction of elaborate instruments, including expansive quadrants, sextants, and specialized astronomical clocks that enabled him to obtain measurements with unprecedented accuracy. The observatory's architecture, influenced by Italian Renaissance designs, harmoniously integrated scientific functionality with aesthetic principles. Additionally, Tycho identified limitations in the initial design of Uraniborg. Recognizing that external environmental factors and structural instability could compromise measurement precision, he established an underground observatory, Stjärneborg. This facility was purpose-built to mitigate the influence of wind and temperature fluctuations, providing a stable platform for advanced instruments and enhancing observational reliability. The subterranean design allowed for more controlled conditions, which ultimately led to a significant reduction in systematic errors during celestial measurements. Tycho's instruments themselves were marvels of engineering. Among these, the large brass azimuth quadrant and the sophisticated sextant demonstrated his acute understanding of the interplay between geometry and practical observation. He innovated methods to calibrate his devices, employing precise techniques such as prostapheresis to perform rapid trigonometric calculations, thereby streamlining the conversion of raw observational data into functional astronomical measurements. These innovations not only increased the accuracy of individual observations, but also contributed to the development of comprehensive star catalogs and planetary tables that set new standards for observational astronomy. The observatories at Hven became centers of collaborative scientific endeavor. Under Tycho's direction, a dedicated team of assistants, craftsmen, and scholars worked tirelessly, exchanging ideas that would lay the foundation for future astronomical theories and technological advancements. Tycho's integrated approach, merging advanced instrument design, empirical observation, and rigorous data analysis, redefined the methodologies of celestial measurement and set a benchmark for precision that endures to this day. Tycho's groundbreaking developments at Hven stand as a monumental contribution to both technological innovation and scientific practice. His pioneering work not only improved the accuracy of astronomical observations, but also established principles that have guided instrument design for centuries. In summary, the Hven observatories exemplify Tycho Brahe's visionary synthesis of art, science, and engineering, a fusion that transformed astronomical research forever. His impact remains indisputably profound. Tycho Brahe's contributions extended beyond observational instrumentation to revolutionary theoretical models. His geoheliocentric system, commonly referred to as the Tychonic model, offered a novel synthesis between Copernican heliocentrism and traditional geocentrism. In this configuration, the Earth remained stationary at the center of the universe, while the Sun orbited the Earth and all other planets revolved around the Sun. Such a model elegantly reconciled the absence of observable stellar parallax with the complex motions of the planets, providing a framework that accounted for both empirical observations and prevailing theological considerations. Tycho's systematic measurements yielded data of unprecedented precision, enabling him to challenge existing astronomical paradigms. By employing advanced instruments and meticulous error correction, he generated star catalogs and planetary tables that significantly reduced observational discrepancies. His commitment to empirical rigor influenced a generation of astronomers and instigated methodological reforms in celestial measurement. Furthermore, his hybrid model formed a critical intermediary step in the evolution of astronomical theory. Although it ultimately ceded ground to the heliocentric models of Kepler and Newton, the Tychonic system served as an essential transitional framework that paved the way for a more accurate understanding of planetary motion. The Tychonic model also exemplified Tycho's interdisciplinary approach, blending geometric insights with detailed observational data. His extensive calculations underscored the importance of mathematical consistency in developing cosmological theories. By proposing a system that was both mathematically robust and observationally verifiable, Tycho set new standards for scientific debate and discourse. His work stimulated further inquiry into the nature of celestial mechanics, inspiring subsequent researchers to refine and expand upon his foundational ideas. Ultimately, Tycho Brahe's Tychonic model symbolizes a critical moment in the evolution of astronomical thought. It represents a sincere attempt to synthesize complex empirical data with established philosophical doctrines into a coherent cosmological vision. This model not only bridged the gap between geocentric and heliocentric paradigms, but also inspired rigorous quantitative analysis that would define future scientific inquiry. Thus, his model remains a pivotal milestone in the annals of astronomical science, indeed exceptionally. Following his groundbreaking work at Venn, Tycho Brahe's career took a decisive turn upon his invitation to Prague by Emperor Rudolf II. In Prague, Tycho assumed the role of imperial court astronomer, where he was afforded unparalleled access to both scientific resources and the patronage essential for continued research. It was during this period that he built a new observatory at Benátky nad Jizerou, further expanding his data collection efforts and refining his measurement techniques. In Prague, Tycho's collaboration with Johannes Kepler, his assistant and devoted disciple, became a cornerstone of his later career. Despite their differing cosmological views, Kepler being an unwavering proponent of Copernican heliocentrism, Kepler greatly admired the accuracy and depth of Tycho's observational data. Kepler's analysis of Tycho's extensive records of planetary motion eventually led to the formulation of his own 3 laws of planetary motion, a breakthrough that has profoundly shaped the field of celestial mechanics. Their professional relationship was characterized by a blend of mutual respect, intellectual tension, and occasional disagreements over theoretical interpretations. Yet it remained intrinsically collaborative. During his final years in Prague, Tycho continued to produce detailed astronomical observations even as his health waned. Plagued by administrative challenges, personal conflicts, and the inherent pressures of courtly life, his scientific dedication never faltered. Instead, he worked diligently, contributing to the compilation of star catalogs and ensuring that his legacy would persist through his empirical methodologies. Ultimately, Tycho Brahe's decision to leave Denmark and establish himself in Prague not only cemented his role as a pivotal figure in the scientific revolution, but also provided a vital foundation upon which Johannes Kepler built his revolutionary laws. His enduring influence is evident in the continuing refinement of astronomical methods and the evolution of modern celestial mechanics. Indeed, Tycho Brahe's enduring legacy transcends his own era, influencing both the scientific and cultural landscapes for centuries. His painstaking observations and technological innovations laid the empirical groundwork for the later advances of Kepler, Galileo, and Newton, fundamentally altering our conception of the cosmos. Today, his contributions are recognized not only through the precise star catalogs and planetary models he developed, but also through numerous celestial features named in his honor, from lunar craters to minor planets. Moreover, Tycho's commitment to measurement accuracy and methodological rigor continues to inspire modern astronomical research, underscoring the timeless interplay between theory and observation. His life has also permeated cultural narratives, being referenced in literature, art, and educational discourse throughout history. As a seminal figure in the scientific revolution, Tycho Brahe exemplifies the enduring value of empirical science in unraveling the mysteries of the universe, a legacy that remains profoundly influential to this day. Absolutely timeless.